Now, coming to the next one, that is enthalpy. As I said you about enthalpy, enthalpy can be also defined in this way also, that the thermodynamic quantity U plus PV is also called the heat content or the enthalpy of the system. The thermodynamic quantity U plus PV is also called the enthalpy or the heat content of the system. I said you already that enthalpy is nothing but known as the heat calculated under constant pressure. We can say that under constant, the pressure remains constant. Alright, so in a particular cylinder, when it is closed, the pressure is constant, isn't it? Clear? So that is the enthalpy or the heat content of the system, which is defined as nothing but H is equal to U plus PV. We can say. Now, let us say that is H1, because as I know that enthalpy is a state function. It's not a path function, it's a state function. So hence, I can calculate the initial enthalpy and the final enthalpy. So initial enthalpy H1 is equal to U1 plus PV1. Now you'll ask me, sir, why not P1? Because pressure remains constant. Remember that enthalpy. P is constant. So P is constant here. It will not be P1, P2. If I am writing P1, P2 means variable, how it is constant then? Alright, try to understand that. Try to understand everything here. So next is, this is your initial enthalpy. H1 is equal to U1 plus PV1. Final enthalpy H2 is equal to U2 plus PV2. Final enthalpy. Now change in enthalpy delta H is equal to H2 minus H1. That is U2 plus PV2. Okay. Minus, that is U1 plus PV1. We can say that. Clear? So we can write it in this way, U2 plus PV2. I can open the bracket and I can write it in this way. U2 minus U1, you can see, if I open the bracket, minus, plus P goes common, V2 minus V1. U2 minus U1 is del U and PV2 minus V1 is del V. So hence I got it, del H is equal to del U plus P del V. Understood now from where I got the formula? I told you, we will derive it. Alright, so del H we can write it as QP and this I can write it as QV. Already said QP is equal to QV plus P del V. Clear? So now this is, we got it. Now one more thing I want to tell you here, that if the work is done in a cyclic process, got it? So in a cyclic process, when the system returns to its original state after the number of changes, then delta U or delta H is equal to 0. Alright? In case of cyclic process, cyclic means when the system returns to its original state after number of steps, we can say that, then delta U or delta H is equal to 0, so to say. Fine. Now that you must remember it in case of cyclic process. Delta U is also 0 and delta I is also 0, and remember it, work done is also 0. Got it? Work done is also 0. Now del U is equal to Q plus W. So if del U is equal to 0, Q is also 0, alright, then work done is also will be 0 in case of cyclic process. Fine. Now we'll find a relationship between, that is the reaction, a particular reaction I'll take it at, alright, between heat of reaction at constant pressure and that at constant volume. What I said, I'll be calculating a relationship between heat of reaction at constant pressure and heat of reaction at constant volume. That means in simple words I should say that I'm going to calculate a relationship. I'm going to find out a relationship between QP and QV. QP and QV. Alright, I'm going to find out a relationship, so to say. QP, I told you just now to you, it is delta H, and QV is nothing but delta U. I've said it already to you. And we also know, just now we came to know the formula, we derived the formula rather, delta H is equal to del U plus P del V. We can say that. Clear? It can be written as. Now, that is, when we are going to, that is, find out a relationship, that is, the conditions should be ideal conditions. The condition should be ideal condition, because what I said you, a reaction, I am going to find a reaction, and it is possible when the gas is an ideal gas, the condition is an ideal condition, where the initial volume is V1 and the final volume is V2. So when I say the condition is ideal condition, then in that case I can write PV1. PV is equal to nRT, so N1 RT. Similarly, PV2 is equal to N2 RT. Got it? Clear? So now here that is volume and number of moles is definitely it is varying definitely because pressure remains constant. In case of an ideal gas, how it is ideal gas? Pressure remains constant because what I said you, I am going to calculate the relationship between QP and QB. Alright, QP and QB. QP is heat calculated constant pressure. Alright, then you can say heat calculated constant volume. If it is constant volume, that's V1 and V2. It is remaining constant. Then the work done will be 0. Then how will you calculate it? So hence I took it the condition as an ideal gas. I took it as an ideal gas. So where I am considering the pressure is constant, R universal gas constant, of course it is constant, and temperature also is constant, so to say. I am considering it. Clear? I am repeatedly saying you. Now here it is PV2 minus PV1 is equal to nothing but N2 RT minus N1 RT. So PV2 minus PV1 is PV2 minus V1. Here RT goes common. It is N2 minus N1. Now for a particular reaction, this N2 stands for, that is nothing but, that is here this is initial and this is the final. That means this is standing for the reactant and this is standing for the product. So here I can write NP minus NR, where P is the product and R is the reactant. I have said you already. N1 is the number of moles for the reactant and N2 is the number of moles for the product. So here instead of N2 I have written NP and instead of N1 I have written NR, number of moles of the product minus reactant. So NP minus NR is delta N, change in number of moles. So it is change in number of moles of gas. I have written it for gas. Why it is you will come to know. G stands for here gas. Alright, and this is your P del V. We can say that P del V is equal to delta Ng RT. Now we know the equation already, we derived it just now. Del H is equal to del U plus P del V. Now when I put this value here, so we get it del H is equal to del U plus delta Ng RT. Del H is equal to, so instead of del H I can write as QP is equal to QV plus delta Ng RT. Then also I can write it down. Okay, so many relations if I give it to you. That is del H is equal to del U plus P del V. Now I am putting the value. Del H is equal to del U plus instead of P del V. What you got the value? This is your P del V, you got it, isn't it? This is your P del V, you got it. You put the value P del V here, delta Ng RT. Where delta Ng is nothing but change in number of moles of the gas. When we calculate the change in number of moles, now we calculate only for gaseous, not for solid or liquid. Why? Because solids and liquids are not compressible compared to that of the gas. They are less compressible. Solid is not at all compressible, so to say. Liquids to a certain extent, but gases are highly compressible, we can say that. So hence, whenever there will be change in number of moles, the change in number of moles will take place in case of gas only. Alright, for example, how to calculate the change in number of moles? For example, you see, I am writing an equation. H2 gas plus Cl2 gas gives 2HCl gas. So here delta N G, alright, is 0. How it is 0? Here number of moles of the product is 2 and number of moles of the reactant is also 2. This is 1, this is 1. So 1 plus 1 it is 2, 2 minus 2 is 0. Done. Now I am taking another equation. C solid plus O2 gas gives CO2 gas. Let me calculate delta Ng here. So delta Ng will be nothing but here 1 minus 1. It is also 0. You will say, sir, this carbon, it's a solid. It's a solid. So what I mean to say to you is that if in a particular reaction liquids and solid is given in the equation, that has to be neglected. We will not consider the number of moles of liquid and solid. We will not consider it. We will consider only for the gaseous. For that reason, I have written it here very clearly. I have written it as G. G stands for gas. So I am going to consider the change in number of moles of gas only. You can see very clearly. This is 1 mole. This is 1 mole. So 1 minus 1 is 0. Got it? I am not considering this, the carbon solid. It's a solid. I am not considering it to calculate the change in number of moles. I already said you the reason. So in this way, what you find is that here, that is delta Ng stands for the change in number of moles of gases. So this is the formula we got it. This is a relationship we got it. That is the relationship between heat of reaction at constant pressure and at constant volume. Got it? At constant volume we got this particular relationship, so to say. Now, when a reaction is carried out in a closed vessel, remember it, when a reaction is carried out in a closed vessel, the volume remains constant. Remember it, del V is also 0. Definitely. When it is carried out in a closed vessel, volume is changing, initial final remains same now. So, del V is also 0 in that particular case, so to say. And the value of R, it depends. If it is SI unit, it is 8.314 joules per Kelvin per mole. The value of R is in case of SI unit, so to say. Got it? In other units, it depends whether it is 0.0821 or 0.083. Got it? So 0.0821 will be what? Liter ATM per Kelvin per mole. And 0.083 will be liter bar per Kelvin per mole. Already we have studied all these things. Got it? So this is about the relationship, so to say, I said. Thank you.